When the species in a reversible reaction are not all in the same phase, only gaseous species and aqueous species, which are species dissolved in water, appear in the equilibrium expressions. Pure solids and pure liquids do not. In the examples given, pure solid carbon, pure solid iron, pure liquid water, and pure solid iron 3 oxide do not show up in the equilibrium constants. Only the gases show up in the equilibrium constants. It so happens that neither equation contains aqueous species. If they did, the concentration of the aqueous species, raised to its appropriate power, ought to be present in the equilibrium constant. The concentration of a pure solid is its number of moles divided by its own volume. Its number of moles and volume remain the same, thus the concentration of a pure solid is constant. This idea also applies to the concentration of a pure liquid. Therefore, in an equilibrium constant expression, for simplicity's sake, each is taken to be 1. They don't affect the reactant amount at equilibrium in a reaction, so they don't appear explicitly in the equilibrium expression. When a reversible chemical equation is modified, we need to use one or more mathematical tricks to change the original equilibrium expression and equilibrium constant into the new equilibrium expression and equilibrium constant. Some examples are shown here. There are two equations given. The first equation shows 1 mole of each of the reactants A and B reacting to give 2 moles of product C. We write the expression of its equilibrium constant, Kc1. Kc1 equals the square of the concentration of C divided by the concentration of A and concentration of B. The other equation shows 2 moles of reactant C reacting to give 1 mole each of products D and E. Its equilibrium constant, Kc2, equals the concentration of D times the concentration of E divided by the square of the concentration of C. Now we need to come up with the equilibrium expression of the third equation, in which 2 moles of reactant C react to give 1 mole of product A and 1 mole of product B. This is the reverse of the first equation. Its equilibrium constant, Kc1 prime, equals the concentration of A times the concentration of B divided by the square of the concentration of C. But how is Kc1 prime related to Kc1? By using our powers of observation, we notice that the terms in their numerators and denominators have swapped places. This means that one is the reciprocal of the other. This is like comparing a fraction 2 over 5 with another fraction 5 over 2. They have a reciprocal relationship. To turn 2 over 5 into 5 over 2, we take 1 and divide it by 2 over 5 to get 5 over 2. To turn 5 over 2 into 2 over 5, we take 1 and divide it by 5 over 2 to get 2 over 5. Whenever 1 is divided by some fraction, we can turn the division sign into a multiplication sign, provided we flip the fraction, that is, make the denominator into the numerator and vice versa. So to express Kc1 prime in terms of Kc1, we take 1 and divide it by Kc1. For the fourth equation, 2 moles of A react with 2 moles of B to give 4 moles of C. We notice that this equation is twice that of the first equation. Once again, we need to write the expression of its equilibrium constant, Kc1 double prime, which is the concentration of C raised to power 4 divided by the square of the concentration of A and the square of the concentration of B. Next, we compare Kc1 double prime with Kc1. The idea is to express Kc1 double prime in terms of Kc1. If we square the numerator and also square the entire denominator of Kc1, we get Kc1 double prime. Since the numerator and denominator share the same power of 2, we can take it out and close the entire fraction of numerator and denominator within brackets and raise this fraction to the power of 2. This just means we are squaring Kc1. For the fifth equation, we notice it is half of the first equation. Now we write the expression of its equilibrium constant, Kc1 triple prime, which is the concentration of C divided by the concentration of A raised to power half, and the concentration of B raised to power half. Again, we compare Kc1 triple prime with Kc1. How can we form an equation involving Kc1 triple prime and Kc1 with Kc1 triple prime as the subject of the equation? We take Kc1 and modify it to make it look like Kc1 triple prime. We take its numerator, the square of the concentration of C, and raise this to the power of half. Similarly, we can make Kc1's denominator resemble that of Kc1 triple prime's denominator. Since the numerator and denominator share the same power of half, we can take it out, enclose the entire fraction of numerator and denominator within brackets, and raise this fraction to the power of half. Raising Kc1 to the power of half means taking the square root of Kc1. Doing so gives us Kc1 triple prime. As for the sixth equation, it looks partially like the first and second equations. Adding all the reactants and products of the first equation to the second equation, we get 1 mole of reactant A plus 1 mole of reactant B plus 2 moles of reactant C to give 2 moles of product C plus 1 mole of product D plus 1 mole of product E. Since 2 moles of C appear on both sides of this equation, they are cancelled off. We are left with a sixth equation. We may write the expression of its equilibrium constant Kc3, which is the concentration of D times concentration of E divided by the concentration of A and the concentration of B. Now we compare Kc1 and Kc2 with Kc3. The idea is to do something to make Kc1 and Kc2 resemble Kc3. When Kc1 and Kc2 are multiplied, the term concentration of C raised to power 2 cancels. This gives us Kc3. Let's see whether we can draw any conclusions from this exercise. Reversing an original reversible equation leads to the new constant being the reciprocal of the original constant. Multiplying an original reversible equation throughout by a factor of 2 causes the new constant to be the original constant raised to that same factor of 2. Multiplying an original reversible equation throughout by a factor of half causes the new constant to be the original constant raised to that same factor of half. Thus, in general, multiplying any original reversible equation throughout by some factor x causes the new constant to be the original constant raised to that same factor of x. Adding two original reversible equations leads to the new constant being the original constants multiplied by each other. Here is an example, given two chemical equations representing reversible reactions as well as their equilibrium constants. At 100 degrees Celsius, we are to calculate the equilibrium constants for the equations in parts A to D. First, we write the equilibrium expressions for the given reactions. Next, we figure out the relationship of each equation's equilibrium expression with the equilibrium expressions of the original equations. Then we make the corresponding change to the equilibrium constant for each. Thus, for the first reaction, Kc equals the concentration of NO raised to power 2 times the concentration of Br2 divided by the concentration of NOBr raised to the power of 2. For the second reaction, Kc equals the concentration of BrCl raised to power 2 divided by the concentration of Br2 and the concentration of Cl2. Notice that the part A equation is the reverse of the original equation 1, where product nitric oxide NO and product molecular bromine Br2 take on reactant roles, and the reactant nitrosyl bromide NOBr takes on the role of a product. So like in the previous example, its equilibrium expression is the reciprocal of that of the original equation. Observe that the part B equation is twice that of the original equation too. Thus, just like the previous example, to get its equilibrium expression, we square the original Kc expression. Upon comparison, we see that the part C equation is half of the original equation 1. It is similar to the previous example, so its equilibrium expression is the square root of the original Kc. Like the previous example, the part D equation is the simplified equation obtained when the original equations 1 and 2 are added. Molecular bromine that appears on both sides of the combined equation cancels. Therefore, to get its equilibrium expression, we multiply the Kc of equation 1 with the Kc of equation 2. By doing so, concentration of molecular bromine also cancels. The magnitude of an equilibrium constant reveals whether products or reactants are favored, so the reciprocal relationship between Kc values of forward and reverse reactions should make sense. A huge Kc value, that is a value that is a lot greater than 1, means that product formation is highly favored. For example, for the reaction of hydrogen ion and hydroxide ion to form water, the value of Kc is huge. The very big magnitude of Kc clues us in on the idea that the product water is favored. Now, even if we were to write the equation in reverse, water is still the favored species. It is therefore the predominant or major species present. Its Kc value, being the reciprocal of the Kc of the original formation of water equation, ought to be tiny. A tiny Kc implies that the reactant water is highly favored. There are different equilibrium constant symbols for different systems. Kc is the equilibrium constant for concentration. We will encounter other equilibrium constants, Ka, Kb, and Kw for weak acid, weak base, and water respectively in the next chapter. Other equilibrium constants such as Kp, Ksp, Kh, and Kf will be covered in another module, Further Chemistry 1, but only some of you will take this module. Please note that while uppercase K is used to denote equilibrium constant, it is also used to represent elemental potassium and Kelvin, a temperature unit. Lowercase k is used to denote rate constant, covered in chemical kinetics, as well as the Boltzmann constant.